if you remember, the problem was, why is it that every time people reduced the magnetic Prandtl number below 1 and got to about a quarter, all these dynamo models on these big supercomputers would simply switch themselves off. And the people were very careful to say, but, you know, we have reduced the magnetic Prandtl number, keeping the Reynolds number fixed. So if these dynamos were supercritical before, they should still be supercritical now. But they were saying, okay, this thing shuts itself off, but nobody was providing an explanation of why that was, that this thing was shutting itself off. Also, there was this issue that we felt, we meaning, you know, this colleague of mine, Stanislav Bolderev, and myself, felt, this shouldn't be right. I mean, it shouldn't be a problem to operate these dynamos in a sort of small magnetic Prandtl number environment, because that's what you got in stellar interiors. It seems absurd that you can't drive a dynamo in a stellar interior. It seems just plain silly. All right, so it turns out that the problem has got nothing whatsoever to do with the magnetic Prandtl number, but everything to do with something called the roughness exponent. So now I have to tell you what the roughness exponent is. Not to be confused with the cancellation exponent. Today's a day of lots of exponents. All right. The roughness exponent is related to something called the longitudinal structure function. So let me introduce you, and we're going to use them a lot later when we get to turbulence. So it's a good thing to define these things. Imagine that you have a velocity v. All right. Here's the velocity at the point x plus r. Take away from it the velocity at the location x. So this thing here is the velocity difference over a length r at the position x. Okay, so it's just a velocity difference. All right, then dotted into the vector r divided by its modulus. So this is a unit vector in the direction of the displacement. All right, so this is the longitudinal velocity difference. Okay, take the modulus of this thing. Okay, the modulus thing is a tricky one. I mean, you don't always take the modulus. In this case, let's take the modulus, okay? Take the modulus of it and raise it to the nth power and do an ensemble average or a volume average or whatever you want average over everything. The quantity that you get, then in an homogeneous isotropic situation, it's only a function of the modulus of r, is called the nth order structure function. Why is it called structure function? I have no idea, but that's what it is, okay? And structure functions are related to things like spectra. So if you take the Fourier transform of the second order structure function, you get the energy spectrum. All right? Okay. For instance, in the inertial range of Kolmogorov turbulence, delta 3, the third order structure function, goes linearly in R. I shall return later to the statement, but, you know, just to give you an example. And if you consider lambda 2, so it's the second order structure function, so it's the square of velocity differences. So it's something related to the energy. Square of a velocity is pretty damn close to an energy. All right? So the second order structure function goes like r to the 2 alpha, then alpha is called the roughness exponent. Okay, why is that? Well, let's suppose that alpha is equal to 1, then the square of a velocity difference just goes like r squared. That's a smooth velocity, because why is that? This is a velocity difference. If this thing here to the power of 1 goes like r, okay, I can divide by r, and then as r goes to 0, that's just the derivative of v. It means that, you know, I can use a Taylor expansion of this thing to find what it is. It's just like the derivative of that times r. So if a function is differentiable, then its first order structure function is linear in L. It's linear in this displacement, in r, whatever. If, on the other hand, is less than linear, then this is a function that is not differentiable. It doesn't have a derivative. The derivative diverges. So this exponent is related to something called the Holder exponent, which is something you use to take derivative of things that don't have a derivative. All right? But it's called the roughness exponent. And the smaller it is from 1, the rougher the process. The more this process kind of oscillates and it's non-differentiable. And the fact that this, instead of being a 3, right? If the velocity, if the third order structure function goes as r cubed, then it's a smooth velocity. In Kolmogorov turbulence, this thing goes as, you know, 1. So it means, oh, Kolmogorov turbulence is pretty damn rough. It's a very, very rough process, okay? It misses having a derivative by quite a bit. All right, so the issue is, if you're trying to drive a dynamo, is it true, is it fair to say that, you know, a smooth velocity or a rough velocity with the same energy are exactly the same thing as far as the dynamo is concerned? Or, you know, the roughness just enters into it? Okay, well, we just derived that, you know, mother of an equation, the Kazantsev equation, so we can just say, what about if I put in a correlator that is, you know, the one that described a rough velocity? Then what happens? I can solve the Kazantsev equation and figure it out. Before I actually solve the Kazantsev equation, because this relates to quantum mechanics, I can get some mileage out of the quantum mechanics and look at it this way. If the inertial range, my velocity has a roughness exponent alpha, then that crazy correlator that I need to construct my effective potential goes as r to the beta, where beta is just 1 plus alpha. Okay? Because this thing has dimension of diffusion, and so it goes like a velocity times the length. The velocity goes like L to the alpha, so this thing goes like L to the 1 plus alpha. Okay? So that's how the correlator behaves in the inertial range. Then if I look at what the effective potential looks like, it's just the potential divided by the inverse mass of the thing, and it's just an 1 over r square potential. So interestingly enough, all of this mess turns into a quantum problem of finding bound state of an inverse square potential. Isn't it funny? Anyway, and the coefficient in front depends on beta. So you have a picture that looks more or less like this. This is your effective quantum potential, okay? This is radius. It goes down as 1 over r, so it's singular. It should go down to infinity. But it doesn't go down to infinity because if you remember, this correlator, wherever it is, okay, had 2 eta. So it's renormalized at small distances by eta. So at small distances, the actual collisional diffusion brings it back up again, okay? So it doesn't go all the way down to infinity. So your potential looks like this, and in the inertial range is somewhere here. Now, beta, the way that beta, this roughness, this alpha, 1 plus beta, whatever, enters it, is that it wiggles this height up and down. Okay? So by making beta, you see, if I increase the roughness, this thing goes further and further up. Okay? And the question is, can I have a bound state in this potential? All right? So if I make eta too large, then eta starts eating up this part. It will move this renormalization that way. So if eta is too big, I don't have a bound state. But if beta is small, you know, this can go down as much as you want. And the roughness just governs, you know, whereabouts this is, up and down. But if you look at it, all right, no matter how you slice it, alpha, okay, this A here, which is what multiplies this potential, right, for no matter what, is always less than a quarter. Okay, it's always down here. And there's a theorem in quantum mechanics that tells you that if that number is less than a quarter, there's always a bound state. All right? You're guaranteed a bound state no matter what the roughness is. It can be as rough as you want. There's always at least one bound state. Here it is. So, conclusion, dynamo action is always, always, always possible. So long as, of course, you have to have a small enough diffusivity. But if your diffusivity is small enough, no matter how rough your velocity, you always get a bound state, which corresponds to an exponentially growing correlator for the magnetic diffusivity. So, whatever it was that these people were finding with their codes, it was not that dynamo action was impossible. Dynamo action was always possible. So what was it that these people were finding? What was the problem? And now is where I really go berserk with the blackboard. Yes. Okay, this is what was going on. Okay, so you have this crazy containing potential, okay? The potential looks like this. Okay, and you have to put a bound state of the potential. All right? Now, the point is that depending where you put this thing, your eigenfunction is more concentrated or less concentrated. Okay, so this is R, this is actual space. Okay, so if your if your eigenfunction is up here, in a sense, to capture that eigenfunction, you need a bigger domain than if this thing is sitting down here. And the thing that moves it from down here to here is the roughness. Okay? So if you have a very smooth flow, your eigenfunction is tiny. It's very localized. And if your roughness is big, your eigenfunction is kind of big. Because if you remember, this thing also tunnel their way out. So, you know, let's say the full eigenfunction is a bit bigger than you think. They oscillate in here and they decay exponentially over there. So the bottom line is this. If you have a smooth flow and you want to work it out numerically, you need a box that is, let's say, this big, if the velocity is smooth. If the same velocity becomes rough, but has the same amplitude, then suddenly you can't fit a growing dynamo in this box. You have to have a box that is much bigger. Okay? So if you don't change the size of the box, what do you see? Suddenly your dynamo switches off, but not because there is no dynamo. It's simply because your box is too small. It's that the dynamo eigenfunction go bigger. All right? It seems paradoxical. And so you can actually draw a diagram that is, what is the numerical resource that I need to capture a growing dynamo eigenfunction as a function of roughness? So if roughness increases that way, then this curve looks like this. Okay, well, actually, I should draw it this way. It goes berserk when alpha goes to 0. At alpha equal to 0, this eigenfunction gets practically enormous. So let's suppose that you're running your code with the magnetic Prandtl number bigger than 1. Magnetic Prandtl number bigger than 1, it means that your dynamo is operating in the smooth regime. So this is what you need in terms of numerical resources. Then you start decreasing the magnetic Prandtl number, and what happens is that your dynamo moves from the dissipative subrange to the integral to the inertial range, and suddenly it's being driven by a rough velocity. And as you transition through PM equal to 1, basically your eigenfunction gets bigger and bigger and bigger. Let's say the Kolmogorov turbulence is here. This to this could easily be a factor of 6 or 7. Okay? In other words, you need a domain that is 6 times bigger in each direction to capture the same problem. Now, most of you know that if you have an explicit code and you're using it in 3 dimensions, all right, the resources go up as the 4th power of the resolution. So if you want something 6 times bigger, is 6 to the 4th power more expensive to get the same answer, which is crazy. You're not going to do it. Bottom line, it's impossible. So when everybody was seeing their code shutting down, it wasn't because there wasn't a dynamo. It was simply because their model for that magnetic Reynolds number was totally inadequate for capturing the growing solution. Okay? So this curve is actually published. But it really is like a factor of 6 going from smooth to Kolmogorov. So you're not going to do it. You're never going to capture this thing. Because it's worse than that, because you have to bear in mind you're working at small magnetic Prandtl number. So to capture the Kolmogorov, you're killing yourself. And then you have to capture everything else that you need to get this damn growing eigenfunction. So it's just crazy. It's like not doable at all. So the numerical problem of doing dynamos in rough velocities is a nightmare. It's a complete nightmare. All right? So, but that problem was put to rest with this issue. It's not that there are no dynamos. Dynamo action in a rough velocity is always possible. It's that you may need very, very large Reynolds number. That's it. Your magnetic Reynolds number goes very high. Okay, so you need these ridiculous resolutions. Okay, jolly good. Any questions about this? Because unless there are any questions, issues, or tissues, I'm going to skip all of this stuff and I'm going to go nonlinear. Any questions? All right. If I not skip that thing, I would have told you that if you take a magnetic field and do the simplest non-trivial dynamic problem on a magnetic field is that of MHD waves. And MHD waves comes in three flavors, the fast, the slow, and the intermediate. And the fast and the slow are waves that are restored both by magnetic effects and pressure effects, and then there is a funny one called the intermediate wave that it's only restored by magnetic tension. So the intermediate wave is essentially incompressible. And for some reason, if you're doing gas dynamics, it's called the intermediate wave. If you're doing incompressible dynamics, then it's called the shear alpha wave. Why that is the case, I don't know. Why they had to have two names for it, no idea. And so what I want to consider now is what happens. Okay, so you say that's linear waves. What happens if you have nonlinear waves? Well, if you have the slow and the fast, they can actually shock. They're compressive waves, so they can lead to MHD shocks. And MHD shocks is really very, very nice. It's a really beautiful theory, but it takes a long time to do. Life is finite, and, you know, Jorge is up to ear of me, so we're not going to do that, but I wish I could. What I'm going to do instead is look at what happens to the intermediate wave, to the shear wave, when it goes nonlinear, because that is what most of us would call MHD turbulence. Okay? So the theory of field-guided MHD turbulence is the theory of the nonlinear interaction of of alpha and waves. And I'll say a bit more about it. So we're going to, change gear a little bit and try to see what is the mathematics and the issues and the tissues that go into this business of describing MHD turbulence. So this is MHD turbulence where you have a mean field. There's a great big mean field, and there are all these waves traveling along the mean field. What kind of turbulence do you get? So this is relevant to the solar wind. Stellar winds are like that. Stellar winds have a great big mean field that is coming out of the stars and all these sort of waves that are propagating along it. And the interstellar medium, also has these magnetized regions that are magnetized on very large scales. And if you look at small scales, that's what you got, MHD turbulence. So what are the properties of MHD turbulence? Now, it's impossible to talk about turbulence with magnetic fields without knowing what's going on in turbulence without the magnetic field. So let me just do at the speed of light the crash course in hydroturbulence. Hydroturbulence hinges on all sorts of hypotheses, but the most important are these. All the similarity hypothesis. There is a number that is the Reynolds number, and all the flows with the same Reynolds number are equivalent. Okay, we've already sort of argued this. There's another equivalent thing to the magnetic Reynolds number. And the fact of life is that at low RE, the flow is laminar, and high Reynolds number, the flow becomes turbulent. And the idea is that if you then look at a time trace of the velocity at a point, it looks an awful lot like a random signal. And when it becomes a random signal, you decide that the only way you're going to describe this quantity, this funny velocity, is by a statistical treatment. So all the theory of turbulence that I know are statistical theories. You don't really care about what the value of the velocity is because it's just a fluctuating quantity. And so in itself, it has no meaning at all. The thing that you want are the distribution functions and stuff like that, the moments, the cumulants, all these good things. Okay, so the evolution equation for the velocity is the Navier-Stokes equation. There it is. Typically, people assume that the divergence is equal to 0, so that is incompressible flow, which means that this pressure here is given by this Poisson equation, and so it has absolutely nothing to do whatsoever with the thermodynamic pressure. So the pressure in an incompressible fluid is just like a Lagrange multiplier that is what you need to solve the equation subject to the constraint that the flow is incompressible. All right? So this thing here is not related in any way to sound waves. It's just what you need. Formally, the sound waves have infinite speed in this equation. Okay? But the bottom line is that the pressure is given by the inverse Laplacian of this thing, and so the Navier-Stokes equation is an integral differential nonlinear equation and is hell to solve. Right? And you can think of it as an infinite hierarchy of moments or cumulant equations, in the sense that if I take the average of that equation, and we've seen that before because we took the average of the Navier-Stokes equation, I find that d by dt of the average velocity depends on the average of products of velocities. So it depends on the variance, and I don't know what the variance is doing. In mean field theory, I could express the velocity, the fluctuating velocity with the fluctuating magnetic field in terms of the mean field. You cannot do this here, because here, everything is nonlinear. All right? But then I can take b dotted into this. Now I have d by dt of v, except that that is now going to depend on triple moments. So in general, the nth order accumulant, the rate of change of the nth order accumulant, depends on the nth plus 1th order accumulant, and so forth and so on, and this thing never closes. And so if I want to be able to solve it at some point, I have to make some assumption that allows me to express the nth plus 1 order moment in terms of everything below it. And that's just an assumption. And different assumptions lead you to different closures of different theories of turbulence. And depending on how you close it and what you assume, you get different answers. And some answers are good, and some answers absolutely are terrible. All right? But none of them are rigorous. There's no way to close this set of equations in a rigorous manner. It cannot be done. So most of the theories of turbulence don't attack the problem trying to say, let me find a mathematically rigorous sequence of operations that give me an equation that I can solve, because it can't be done. So that would be futile. So instead, what you do, you invent some kind of mathematical object, a phenomenology that you say, this is a much smaller problem that I can deal with, and somehow it informs me about what's going on in turbulence. So most of turbulence proceeds that way. We make little games in our head and say, ooh, turbulence to me looks just like this. And where this is a thing that I understand, rather than this god-awful equations that no one can solve. All right. So one of the most useful and commonly used things is this idea of a cascade. So what is a cascade? The cascade in hydroturbulence comes about because of this. If you look at this term here, the effect of this term is the following. If you have energy at a given wavelength, that term will redistribute the energy to terms with different wave numbers. So the u dot grad u terms, these nonlinear terms, redistributes energy amongst all of the other wave numbers. So it spreads it around. So if you start with everything a big scale, u dot u will try to generate bigger scales and smaller scales. Okay? There's also this term here, which of course looks linear, but it's not, because this is the inverse Laplacian of this mess, of the divergence of that. And you can show very easily that that term does not redistribute anything amongst wave numbers. So big things remains big and little things remains little. But what it does is it spreads everything around amongst the directional components. So if you have flow that is mostly going that way, the effect of the pressure term is to take all the energy going that way and to try to redistribute it into energy going that way and that way, until eventually you have about the same amount of energy going in all three directions. So this thing drives a cascade, and this guy drives a cascade towards isotropy. So the effect of the pressure term is to isotropize the cascade. Okay? That is not always the case. It will definitely not be the case in MHD. Okay, so one of the big assumptions is that a large Reynolds number, there's a range of scales whose dynamics is independent of viscosity, because viscosity is assumed to be tiny, and large-scale forcing and boundary conditions don't matter. So if boundary conditions don't matter, forcing doesn't matter, viscosity doesn't enter, nothing matters. It's only the mathematical structure of the Navier-Stokes equation that matters, because there's nothing left. That being the case, the dynamics in this thing called the inertial range should be universal. Okay? Should be the same for all the flows with the same Reynolds number. And then you could say, okay, if this thing actually exists, what exactly does it look like? Now, what am I plotting here? I'm plotting EK as a function on K. So this is wave number, inverse scale, large scales, little guys. So down here, there's the dissipative subrange, which is where dissipation comes in. These things are called the integral scales, which is where non-universal things act, like you stirring the fluid or some boundary conditions or God knows what. And in between, there is this inertial range. And what I'm plotting here is what is called the energy spectrum function, which is the amount of energy at that wave number. Okay, so if you integrate this thing dk, you get the total energy of the flow. And what everybody wants to know is, what is the behavior of the energy spectrum in this range. And why is that? Because in general, the first moment is trivial. It's just the average velocity. You can have that the average velocity is 0, so who cares about that? So the first non-trivial moment is the second order moment, is the variance, and the variance is related to the energy spectrum. Okay, so the energy spectrum, it's an encoding of the second order moment. Okay, I have a colleague that says, in turbulence, there's only two useful results, and they're both by the same guy. And, okay, what is my colleague talking about? In 1941, Kolmogorov wrote two papers, very, very short, that had a long and fundamental impact on the field of turbulence. And these two papers are called the 4/5 law, Kolmogorov 4/5 law, and Kolmogorov spectrum. And what exactly do they say? Okay, important thing. The 4/5 law is exact. All right? No approximation, no nothing. He just took the Navier-Stokes equation, mucked around with moments, and got this result. That the third order structure functions, remember what those things were, take velocity differences, raise them to the third power, ensemble averages anyway, is minus 4/5 epsilon times r plus all sorts of stuff that depends on the viscosity. In the inertial range, the viscosity is 0, so this goes away. So in the inertial range, the third order structure function goes linearly with r. Okay? So this is what I was saying before. The Kolmogorov turbulence is very, very non-differentiable in the inertial range. And this is exact. Okay? With a minus. Even more bizarre. Okay? Which means that energy is going to small scales. Okay. So this is one paper, 4/5 law. This is the Kolmogorov spectrum. In the inertial range, the energy spectrum goes like some constant, Kolmogorov constant, epsilon to the 2/3. Epsilon is the energy dissipation energy dissipation rate. Wave number to the minus 5/3. Okay? So this is, everybody knows it. They know it in kindergarten. That in the inertial range of homogeneous isotropic turbulence, the energy is like k to the minus 5/3. This is phenomenological. This is not an exact result. Okay? I'll show you in a second how we got it. But this is a piece of phenomenology, whereas this is exact. But notice that these two are actually compatible. Why is that? I mean, if you had a phenomenology that was incompatible with an exact result, it wouldn't be very useful, let's face it. It's compatible in the sense that if I could take the cube root of this thing, if I could apply dimensional analysis to it, I would conclude that the first order structure function goes as r to the 1/3, so the second order structure function goes as r to the 2/3, and then if I take the Fourier transform of that thing and I integrating over a shell, I get k to the minus 5/3. So these two results are compatible. Okay? One implies the other. Provided that they are very small intermittency correction, because in general you cannot take, it's not true that the average of something is, the square root of the average of something squared. It's not true in general. It's only true on certain circumstances if there's no intermittency. Okay, so let me show super fast how you get the Kolmogorov spectrum. You assume the following thing, that the turbulence is homogeneous isotropic in the inertial range. Is that justifiable? Well, yeah, because pressure drives everything towards isotropy. So if you wait enough, this thing becomes homogeneous. It becomes isotropic. Oh, okay, it's quasi-stationary in the sense that, yes, turbulence is always decaying or doing something, but you have to bear in mind that the interaction time for the small scale is much, much shorter than the interaction time for the large scales. So in the time it takes for the large scale to decay, the little guys have interacted 1 million times. So from the point of view of the little guys, you're almost in a stationary state. Okay? And then this business of locality in phase space, which is a kind of technical issue, that says that the interaction between eddies is strong only for eddies of comparable size. So the interaction of a gigantic eddy with a tiny one is nothing, because it's just mean advection. And since this equation is translationally invariant, it's just like moving the whole thing around. It doesn't do anything. It doesn't contribute to the transfer of energy. Okay, if you believe that this thing is quasi-stationary and energy is flowing through in my cascade, it has to flow through at a constant rate, because otherwise it would pile up in a place, and then this place would get all the energy, and it wouldn't be a quasi-stationary state. So the energy transfer rate is just the square of the velocity at a scale lambda divided by the time it takes for the energy to cascade from the scale lambda to the next scale. So this energy transfer rate should be constant. All right? This is the velocity difference across the scale lambda. All right? Then you say, what is the characteristic transfer time at the scale lambda? Well, you have no scales other than the turnover time. So you say, well, it's just the turnover time. It's also, you can write it in different way. Is the turnover time, is the time to deplete the energy from the scale of psi lambda, or if you want to be really, really fancy, you say it's the decorrelation time for triple moments of the scale lambda. Because the triple moments are the one that govern the transfer, the rate of transfer of energy. Energy is a quadratic quantity. The energy transfer rate is a cubic quantity. Okay? So it's the time it takes for those triple moments to decorrelate. All right? It's well known empirically that this thing is just lambda over v lambda. So if you put the lambda squared lambda over v lambda is equal to a constant, v cubed is over the lambda. See, this is consistent with the famous Kolmogorov 4/5 law. We knew that all along. All right? But this is compatible with it. All right? And if intermittency is weak, well, I can take, the 2/3 root of that thing, and then, v squared goes like lambda to the 2/3. I take the Fourier transform, and I get k to the minus 5/3. Exactly as advertised. Okay? I have to, assume that I can go from this to this. But in general, this is not true because of intermittency correction. So if you read 97% of the current papers on turbulence, everybody's obsessed about the little corrections to 5/3 that arise from intermittency. And one of the prevalent model that is used to understand the origin and nature of this little correction is something called the multifractal model, which is due to Parisian Frisch. And so if you like fractal geometry and fractal crazy stuff and all of those things, by all means, look up, the multifractal model of turbulence, which is actually a lot of fun to play with. But we're not going to be concerned with intermittency correction because most of the issues in MHD turbulence is not the deviations from the spectrum, is what is the spectrum in the first place. So MHD now is where hydroturbulence was in 41. All right? That's, that's the difference in understanding one as opposed to understanding the other. All right. Quick notes. If you have a power law spectrum, is indicative of a process with no characteristic scale, which is exactly what you expect, because neglecting diffusion, the Navier-Stokes equations, become the Euler equation, and the Euler equation is scale free. Now, if you go back and check the way that I derived this thing, you will notice that the time of this tau thingy that I put in there measure the strength of nonlinear interactions. Okay? So a turnover, it means the nonlinear interactions are very strong. In one turnover, they completely destroy an eddy. Okay? They couldn't be stronger. All right? So TK, even proportional to the turnover time, is a very, very strong interaction. And in general, the stronger the interaction, the deeper the spectrum, the weaker the interaction, the shallower the spectrum. So if you start messing around with this thing, you change the spectrum of the turbulence in the inertial range. Okay? All right, back to MHD. All right, now you know how to play this game, so now we're going to play this game with MHD. So, MHD what? Okay, first of all, we're going to measure everything in units of the Alfvén speed. If I do that, B and V have the same unit. They're both velocities. Okay, so magnetic fields and velocities are both measured in units of velocity. I'm going to assume that there is a uniform background field of strength VA. And it's strong. So I've got this great big uniform field. For the hell of it, incompressible flow. And then if I linearize about this, uniform field set V equal to 0, in the incompressible case, I get two sets of modes, okay, that are called the shear alpha waves, which are the intermediate wave in a compressible fluid, and the pseudo alpha wave, which are the incompressible limit of the slow waves. And the only difference, they have exactly the same dispersion. Here it is. That's the dispersion for these things. And all this thing is saying, if you look at it, is that alpha waves travel at the alpha speed. You know, big deal, hence the definition. Okay? And so the difference between this and this, it's just the polarization vectors between the shear alpha waves and the pseudo alpha waves. And the way that the shear waves look like is that if this is my magnetic field, okay, and this is K, so let's say going in this direction, then the polarization is this way. So they wiggle this way while they propagate that way. Okay? Whereas the pseudo ones, where are the pseudo ones? There you go, those guys. All right? Then, you know, if this is the mean field and this is K, then the displacement is this way. It's in the same plane. The polarization is in the same plane, but it's perpendicular to K. So it's like this, and they would be wiggling like this. All right? And between the pseudo waves and alpha waves, I have a complete set, so I can do all of MHD turbulence in terms of pseudo alpha waves and shear alpha waves. All right? And it's worth knowing that there are 3 invariant quantities. 2 of them you've already met. You've already met, well, you know that the energy is conserved by ideal MHD. We've discovered that the helicity is conserved in ideal MHD, but there's also another one called the cross helicity, which is V dot B. Not A dot B, but V dot B. So this has got the correlation of the velocity and B. So this is something that measures the degree of alignment of the velocity and the magnetic field. Remember, this is the energy. Everybody, this is positive definite. These are signed indefinite. And it's known that this cascades to small scales. This cascades to small scales. This, God knows what it does. But if it does anything, it cascades to large scales. Or so it would seem. Okay? If you're no longer sort of... okay. And what we're going to do is assume that there is an inertial range. If there's an inertial range, what does it look like? Can we play the same game that we could play before? Okay. It is customary at this game not to solve the induction equation and the Navier-Stokes equation, but to define this funny variable called Elsasser variable, Z plus and minus, which is just V plus and minus B, where B is the fluctuation relative to the mean field. Okay? So this is a fluctuation, that's a fluctuation. And if I introduce this thing, stick it back, muck around with the Navier-Stokes equation and induction equation, I'm going to get 2 equations that look like this. Okay? Dissipative terms that I don't care about because I'm interested in the inertial range. And notice that there are two terms. The rate of change of these things, VA dot grad. So each one of these variables is advected along the mean field. So the mean field takes little fluctuation in Z plus and Z minus and just kind of moves them along, one this way and one the other way. All right? And the other one is a nonlinear interaction, Z minus, Z plus, Z plus, Z minus, which means each one of the fluctuations interacts with the other one. Okay, so the Z plus interacts with the Z minus, with the Z minus with the Z plus. Okay, so you have 2 interaction terms, a linear one, which is VA dot grad Z, and Z dot grad Z. Okay? And what you get as the answer depends entirely, 100% on what you think is the dominant thing. So if you think that the dominant thing is the linear interaction, you get a theory. And if you think it's a nonlinear one, you get a different theory. And if you go for a mixture of the 2, you get a mixture of the theory. Okay? So suddenly things are not as obvious as they were in hydroturbulence because you've got options. Okay? Now, the important thing to notice is the following. Suppose that you don't have any Z plus. Then it's very easy to show that if Z minus is any function of R minus VAT, then it's an exact solution. All right? And it's a right propagating wave. And likewise, if Z minus is equal to 0, any function of R plus VAT is also an exact solution. So the conclusion is that a pure right propagating alpha wave is a nonlinear solution of the equation. And a left propagating shear alpha wave is also an exact solution of the equation. So you're not going to get any transfer of energy whatsoever if you only have waves that propagate in one direction. So the theory of MHD turbulence, it's all about the interaction of counter-propagating wave packets. You have to have a wave going this way, a wave going this way, they whack into each other and they interact. If you just have stuff going that way, it will not interact. If it's stuff going that way, it won't interact. So alpha waves are not self-interacting. They don't steepen, they don't form shocks. Okay? All right. All right, so the property of the inertial range depends on who dominates on what. Wow, I'm running out of time. So let me show you the original theory of the stuff, which is due to Eroshnikov and Kraichner. So this guy wrote it in the 60s, mid-60s, 70s, in complete analogy with what was going on with Kolmogorov turbulence. So they knew perfectly well Kolmogorov theory, and they said, let's do the same thing to MHD, see what we get. And so, of course, the first thing they assumed is that, first of all, the linear interactions dominate and the cascade is isotropic. Is that a good idea? Who knows? But that's what they assumed, an isotropic cascade. Okay, then they said, look, VA is very large, so these wave packets are moving through each other at the alpha speed. All right? So here it is. When they move through each other, they interact. But the time they have to interact doesn't depend on how big they are. It only depends on how much time they have to interact with each other. That depends on the alpha speed, depends on the mean field. So if the mean field is huge, these guys are only going to go through each other for a very, very short time. So they're hardly going to interact at all. So the Eroshnikov-Kraichner theory is a kind of weak turbulence theory, because it assumes that in a wave packet, the distortion is kind of small. All right? So the typical distortion would be v squared over lambda, because you have a term which is like v dot grad v. So it's two v's and a, and a 1 over lambda. But they decreased it by the time it takes for these things to go through each other, which is very, very short. So they don't interact for very long. So in one collision, you don't really cascade an awful lot of energy. You need lots of these collisions. Let's say you need n of them. And you say, how big does n have to be so that the distortion is of order 1? And then you say, well, it depends, because it depends if you're adding these things coherently, then they just add. Or incoherently, then they add, and you have to go as a random walk, as the square. And they said, well, it's an incoherent adding. And so if you say that n is what you need to achieve a substantial distortion of a wave packet in incoherent interactions, then that's the number you need. VA over lambda thingy. All right? Okay. And so the energy transfer time, so the time that it takes you for all these n interactions to take place, is given by this formula. Here it is. It's one interaction times these, incoherent adding thing. So now I can play my game. I just say that the cascade, so this is VA squared divided by time Eroshnikov-Kraichner is a constant. This gives you that the velocity, velocity difference of the scale lambda goes like lambda to the 1/4. So the energy spectrum is k to the minus 3/2. Okay? So the conclusion is that in the Eroshnikov-Kraichner theory, the cascade remains isotropic. The turbulence again becomes weaker and weaker and weaker. And the spectrum goes as 3 to the minus 1/2, not 5/3, which is the Kolmogorov one. Now, in the early 90s, people were beginning to say, this is silly. I mean, there's absolutely no evidence at all that the turbulence, MHD turbulence, remains isotropic. I mean, look at this thing. You have this great big mean field, everything kind of getting elongated this way. How on earth can you invoke a turbulence cascade that is isotropic? All right? So Peter Goldreich and Sridhar came along with a theory, with a phenomenological theory of turbulence that was non-isotropic. Okay? So they assumed the following things. Cascade is not isotropic. So the rate at which you cascade along the magnetic field is different than the rates that you transfer energy transverse to the magnetic field. And most of the energy transfer, they said, is transverse to the magnetic field. Okay? Okay, the transfer is mediated by the shear alpha waves. Why is that? Because they are the ones that have the polarization transverse to K and B. All right, so they are the ones that are good at transferring energy transverse to the magnetic field, to the mean magnetic field. All right, the turbulence remains strong at all scales. What does that mean, strong? It means that these linear and nonlinear terms have to be roughly comparable. So in the time it takes for two wave packets to go through each other, basically they've interacted. One collision. The other one you needed n of them. This one you only need one. Okay? And so L is the longitudinal size of a wave packet. Lambda, like before, is the transverse size, but it's the coherence length of these things. Okay? So we have now two scales, L and lambda. So think of a wave packet as something like an elongated sausage that is about this long L and this wide lambda. Okay? And they're going through each other. Splump. Okay. And the wave packet is substantially distorted in a single interaction. What does that mean? Okay, this is the time it takes for these two wave packets to go through each other. And so that has to be the same as the turnover time transverse in the transverse direction. Okay? So this relationship that, you know, transverse velocity to transverse scale, longitudinal scale alpha and speed, is called the critical balance condition. And they just asserted that it was true. Okay? And that corresponds to a balance between the linear and nonlinear terms. Okay, at this point, you know, we have the transfer time for the Goldreich-Schrödinger thing is just L over VA, which is of the same order as lambda over V lambda. So proceed as before. By the time we finish, we will have done this a million times. And what you get is that, well, this is essentially the turnover time transverse, and so V lambda goes as lambda to the 1/3. Conclusion, the energy spectrum in the Goldreich-Schrödinger thingy is K perpendicular to the -5/3. So it's the same as Kolmogorov theory, but it's not with a wave number, it's with the transverse wave number. Okay? And since L goes as lambda to the 2/3, okay, these things, as lambda becomes small, so you see, L is going to 0 slower than lambda. These things are getting longer and longer and longer. So the picture you have to have in your head, that you start with two blobs that are more or less spherical, two wave packets. They go through each other, and they've become much smaller in the transverse direction and elongated. Then they do it again. They become much smaller and very long. And as it continues, this thing, eventually you get a spaghetto. Okay? You start off with a gnocco, and you end up with a spaghetto. This is my Italian background showing up. All right. So the bottom line is then the Schrödinger theory, the cascade is strong at all scales. It's anisotropic with most of the energy being transferred transverse. And the anisotropy gets worse and worse and worse as you go to smaller scales, which is completely the opposite from hydroturbulence, where as you go to small scale, you establish isotropy. All right. So by the so you have these two very different pictures of this thing. One, you know, the velocity goes as lambda to the 1/4, velocity goes as lambda transferred to the 1/3, the spectrum 3/2, spectrum 5/3. Weak, isotropic, strong, and isotropic. They're completely different. And so in the 90s, computers got big enough that, you know, we could actually go ahead and say, well, you know, who's right around here? Which is a better model for what's going on? So we started running this big simulation of MHD turbulence. And of course, we found that sure enough, Goldreich and Schrödinger were correct. There was very, very strong anisotropy. So, you know, the Goldreich-Schrödinger theory looked like a much, much better theory than the eruption of Kreiknan. And the spectrum was almost bang on 3 to the -1/2. So you're going to say, wait, hold it. That's the one that goes with the wrong theory. So we have the theory, spectrum from one theory, anisotropy from the other theory. And of course, you know, in the beginning of the 90s, these computers weren't that big. And so you say, well, maybe when we go to higher Reynolds number and all this thing is going to change slope. So, you know, we went to bigger computer, bigger simulation, bigger this, bigger that. And sure enough, this spectrum went closer and closer and got bang on 3/2. Okay, so by the 2000, it was obvious that the spectrum was -3/2 and not -5/3. So why was it that the better theory predicted the wrong spectrum? What on earth was going on? Okay, so in the next 10 minutes, I will try to fix this theory for you. And in order to fix it, I will have to introduce what is now known as the theory of scale-dependent dynamical alignment, okay, which is what I believe is the current model of MHD turbulence. All right, which is a mixture of everything. okay, so what is the problem? The problem is that you expect the spectrum to be k to the minus 5/3, k perpendicular, minus 5/3. And it's not. It's k to the minus 3/2. So it's shallower than you expect it to be. Yeah. But we said, you know, if you get a spectrum that is shallower than what you think, you know how you fix it? You just say that the interactions are a little bit weaker than you thought. Because, you know, as soon as you have a weaker interaction than what you think, then your spectrum gets a little bit shallower. So I can fix this problem. I can just fix it. Then I can think about what have I done to fix it. So what we're going to do is fix it first and ask questions later. So let me fix the problem, and then we try to figure out what we've done. Okay, so the idea is that, you know, these damn nonlinear interactions, here they are, they're not as strong as I thought they were. For some reason, there's some physical process that is preventing energy from being transferred the way it should be transferred. And so there must be a depletion factor for the energy transfer rate. And let me just encode it like this. Ratio of the alpha in velocity to the velocity of scale lambda to the sum power alpha, to be determined later. All right? Then I can go through all these contortions. The energy transfer time is what I think, you know, increased by this depletion factor. It's going to take a little bit longer. I put it into my cascade. So here's the time scale with the depletion. Go through all of these things, and I find that the velocity scales like lambda to 1 over 3 plus alpha. Tau goes that. L goes like that. So I get the scaling of everything, and they're all alpha dependent. Okay, they depend on this, you know, how much I think is the depletion rate. All right? But notice that if I put alpha equal to 0, okay, then I get I get the Goldreich-Schrieder one. And if I put alpha equal to 1, I get the right spectrum. So with a depletion rate of alpha equal to 1, I can get the right spectrum within the Goldreich-Schrieder kind of sort of theory. All right? So the question is, okay, well, why is alpha equal to 1, or even what on earth does alpha equal to 1 mean? Who's depleting what around here, okay? So let's try to figure out the physical mechanism that could deplete the nonlinear transfer, all right? So consider okay, first of all, you have to think about one thing. What's interacting here are shear alpha waves that are very strange creatures, because there are these creatures that their polarization, so their amplitude, is always perpendicular to k. All right? And the nonlinear interaction terms are of the form z plus dot grad z minus. Okay? So you want to know the rate of change of z minus along the direction of z plus. Okay? But the amplitude of z plus and z minus is always perpendicular to their k. So you can ask yourself, what happens if z minus and z plus align? If they have the same, you know, if their polarization aligns, what happens? You know, the nonlinear transfer goes to 0. Because then z plus is in the direction of k, and that's 0. So we can begin to suspect that there may be a mechanism that suppresses this thing that has to do with alignment. But, you know, let's figure it out. In the Goldreich-Schrieder theory, wave packets are completely homogeneous. So this is the mean field, and if you look at them, they wiggle in all directions. So their polarization is just going all over the place. All right? But let's suppose, you know, just for the hell of it, suppose that you take one of these wave packets and you squish it sideways so that the polarization look like this. That they're predominantly in one direction. Okay, because they're squished. So now I have introduced yet another quantity, which is, you know, lambda is this way, and then I have, you know, an epsilon that way. Okay, so I have, you know, the length, the width, and the other semi-axis. Let's call it psi. What determined this thing? Well, psi is related to the amplitude, because it's how much one of these waves deviates from being dead straight. It's just the amplitude of delta B. Okay, so psi is like the amplitude of delta B. And I can work it out, and it goes like this, okay? From all the scalings that I have. So if the transverse elongation is strong, so these wave packets are squeezed a lot, the polarization vectors z plus and z minus become aligned to within a little angle, that, you know, theta, call it what you like, where tangent of theta is the transverse coherent size of this wave packet times the amplitude. So it's given by this. And if theta is much less than 1, tan theta is almost theta, so theta goes as alpha to the 3 alpha, alpha divided by 3 plus alpha. Okay? So if the polarization vectors are aligned to within a small angle theta, nonlinear terms from the interaction of shear alpha waves are correspondingly reduced by an amount theta. So this thing, because of the geometry of shear alpha waves, is not equal to what you expect, but it's equal to what you expect times the depletion factor of theta that scales in this crazy wave. Alpha with 3 plus alpha. Okay? But wait a second, that was exactly the rate of depletion that I needed to fix this problem. So if these things get aligned with, with an angle that scales like I said, then this thing can be the mechanism that I was looking for to deplete my nonlinearities. So I can deplete at the right thing, provided, I have this alignment that has this funny scaling with alpha. Okay? Notice, however, that in some sense, the above picture is valid for any alpha, but it's only alpha equal to 1, which gives the correct agreement. So it will deplete anything, but sort of why is it alpha equal to 1? What's so good about alpha equal to 1? Why is it that this angle has to scale in this crazy way? All right? So, let's just think about what we're doing. We're saying, in the Goldreich-Streeter picture, everything gets elongated, but it's isotropic in the transverse direction. Then I'm saying, if for some reason, as yet not better specified, this thing, when it cascades, not only it gets elongated, but it also gets squashed. So long as it gets squashed at some right rate, okay, then I can get the right spectrum. But then the question is, why is it getting squashed at exactly that rate? What's so good about that rate as opposed to any other rate of squishing? Okay, so we have to find some geometrical reason why that is a good stretching rate. All right. Now, what we've been talking about here is the alignment in the cross-perpendicular direction, okay? But the total alignment, all right, is actually the alignment in the longitudinal direction plus the alignment in the cross-perpendicular direction. And the sum of the two is the total alignment. Okay? But the total alignment has something to do with V dot B, with the cross-helicity, which is another one of the invariants of this theory. Now, the Goldreich-Streeter theory doesn't know anything about cross-helicity. It just uses energy cascade. It just says the energy has to cascade uniformly through the scales. It hasn't done anything. It hasn't used the fact that there's also these other invariants that I have to do something with. Okay, so let's suppose that I do something with these other invariants. I make a statement about this other invariant and say, I want this other invariant to be maximized. I want this thing to be as big as possible at every scale. Align everything. And you say, no, you can't align everything. Because if you align everything, then you have one of these exact solutions and nothing cascades at all. So perfect alignment is not possible. Perfect alignment is incompatible with an energy transfer. Okay, so you say, okay, then we'll do the next best thing. We do a maximization of the alignment at every scale, subject to having an energy transfer rate that is constant. So I align as much as I can while still letting this poor energy go down to small scales. Okay? So it's the best thing that I can do with the cross-helicity and still have energy cascade to small scales. Okay? If I try to do that, I can do it, as a variational problem, but it's actually easy to do. You can show that the mismatch in the cross-perpendicular direction goes as lambda to the alpha 3 plus alpha. In the perpendicular direction goes as 1 over 3 plus alpha. So if I look at the total mismatch is given by the square root of the sum of the square. Oops, there should be a square here. Sorry about that. This is 2. Okay. So if I try to maximize that thing, I find that if I let alpha go into infinity, I minimize this one, but I maximize that one. If I let alpha go to 0, I minimize that one, but I maximize this one. And so you say, okay, which is the one that minimizes everything? Is when the two of them are about the same. And the two of them are about the same when alpha is equal to 1. So alpha equal to 1 is very, very special. It's the one that maximizes the alignment at all scales while preserving a constant energy cascade. Wow, I did it. Okay, so let me just conclude. So basically, this theory here makes two predictions. Well, makes all sorts of predictions. But the most important predictions is that it tells you what the angle of alignment, well, it tells you what the spectrum is. It's 3/2. We already knew that the spectrum was 3/2. That's why we invented this crazy theory in the first place. By the way, the guy that introduced this crazy idea of the dynamic alignment is none other than Stanislav Boldyrev. That is the same guy that I was talking about before. This guy is phenomenal. If you want to see phenomenal people, invite him to give a talk. But anyway, so he's the one that conceived of this theory. But the great prediction of this theory is there is this alignment angle, and this alignment angle is the scale as lambda to the -1, to the 1/4. So the angle gets smaller and smaller and smaller as you go to small scales. And this is the angle between the polarization vector of delta V and delta B. So these things are trying to become perfect alpha waves, but they never quite make it. But they get closer and closer to it. And the interesting thing is that in this picture, your dissipative structures, instead of being spaghetti, like I said before, they actually turn into linguine. So they get squished this way. So you start with a gnocco and you end up with a linguina. Okay? So this is the picture. It's not to say that all these linguine are aligned. These things are all random. So there is no preferred orientation on average. But in each, let's say, packet will get squished that way. And it makes this prediction that the sort of, the squishing should go as theta to the 1/4 power. And by now, we've run, I don't know how many numerical simulations, and, things up to almost, 2,000 cube. And if you measure the alignment angle, this thing goes straight down as L to the 1/4 power. So insofar as any of us can tell, we've not been able to find anything wrong with this theory yet. All of the prediction of this theory have worked. The elongation rate, the alignment angle, the spectra, they're all correct. Maybe later we're going to find that this screws up something else that we don't know what. But so far as I can tell, this theory is about the Goldreich-Schrieder theory supplemented by, this dynamic alignment thingy is about as good as it gets. And the interesting thing is that partly as a result of this theory, people have started measuring polarization alignments in the solar wind, and they do find that it's scale dependent and it's compatible with 1/4. So this may actually be a good thing. And with that, I bid you farewell, goodbye, and I thank you for listening for so long. All right, thank you very much. Yeah, I'm here until Friday.